I've been thinking a lot about stars lately, and it's one of those things that seems so permanent, so eternal, that we barely even question it. You look up at night and there they are, scattered across the darkness like they've always been there and always will be. And that's what humans have thought for most of our existence, right? The stars were literally called the fixed stars by ancient astronomers because they seemed unchanging, immutable, eternal markers in the heavens. But here's the thing. Here's what keeps me up at night sometimes. They're not eternal at all, not even close. Every single star you've ever seen, every point of light in the night sky, every one of them is going to die. And I don't just mean die eventually in some abstract far-off way. I mean the universe is heading toward a future where there will be no stars at all. None. Complete darkness. And that future, well, it's as certain as anything in physics can be. And what makes this so strange, so unsettling really, is that we're living in what you might call the golden age of stars. Right now, in this moment of cosmic history, the universe is absolutely filled with them. Hundreds of billions of galaxies, each with hundreds of billions of stars, all burning, all shining, all pumping energy out into the void. But this moment, this era we're in, it's just a blip. It's a brief, brilliant flash in a much longer story, and that story ends in darkness. Total, complete, absolute darkness. And when I say the stars will disappear, I don't mean they'll move somewhere else or hide behind something. I mean they will cease to exist. The universe will become a cold, dark, empty place where nothing burns, nothing shines, nothing even moves very much. And the really strange part, the part that's hard to wrap your mind around, is that this isn't some catastrophe or disaster, it's just physics. It's just the natural consequence of the laws that govern everything, playing out over timescales so vast that they make the entire history of human civilization look like less than a blink. You see, when we look at stars, we're seeing something that feels permanent because it operates on timescales so much longer than human life. The sun has been burning for 4.5 billion years. 4.5 billion. That's longer than the Earth has had continents, longer than life has been complex, longer than anything we can really comprehend in human terms. And it's going to keep burning for another 5 billion years or so. But here's the thing, even the sun, even our stable, middle-aged, ordinary star, it's going to die. And when it does, well, it's not going to be pretty. But we'll get to that, because to understand why the stars will disappear, we need to understand what a star actually is, what keeps it burning, and why that can't last forever. So let's start with what a star is doing, right? Because when you look at a star, you're not seeing something that's just sitting there glowing like a light bulb. You're seeing something much more violent, much more extreme. A star is basically a massive ball of gas that's so dense, so compressed by its own gravity, that the core reaches temperatures of millions of degrees. And at those temperatures, something remarkable happens. Hydrogen atoms, the simplest element, they start slamming into each other with so much force that they fuse together. They combine to form helium, a heavier element. And when that happens, when those hydrogen atoms fuse, they release energy. Enormous amounts of energy. That's what Einstein's famous equation E equals mc squared is really telling us, that a tiny amount of mass can be converted into a huge amount of energy. And stars are doing this constantly every second, fusing millions of tons of hydrogen into helium and releasing the energy that makes them shine. And this is what's keeping the star alive, what's keeping it from collapsing under its own weight. Because here's the thing about gravity, it's always trying to pull everything together, to crush matter into the smallest possible space. A star is this incredible balancing act between gravity pulling inward and the energy from fusion pushing outward. As long as the star is fusing hydrogen in its core, it produces enough pressure, enough outward force to balance gravity. It's stable. It's in what physicists call equilibrium. But, and this is crucial, but that equilibrium can't last forever, because eventually, inevitably, the star runs out of hydrogen to fuse. It runs out of fuel. And when that happens, well, the balance tips. Gravity wins. And that's when things get interesting, when stars start to die. Now, the way a star dies, the specific process, it depends entirely on how massive it is. And this is where things get complicated, where the diversity of stellar death becomes apparent, because not all stars are created equal. You have stars that are just a fraction of the sun's mass, tiny red dwarfs that burn their fuel so slowly, so economically, that they can last for trillions of years. And then you have massive stars, giants that are 10, 20, 50 times the mass of the sun, that burn through their fuel in just a few million years. And between these extremes, you have every variation you can imagine. But all of them follow the same basic pattern. They fuse hydrogen until they can't anymore, and then they either find another way to keep burning or they collapse. For stars like the Sun, medium-sized stars, the death process is relatively gentle, at least by cosmic standards. When the Sun runs out of hydrogen in its core, about 5 billion years from now, it's not going to just wink out. No, it's going to get bigger, much bigger. You see, when the core runs out of hydrogen, it starts to contract because there's nothing to hold it up anymore, nothing to balance gravity. And when it contracts, it heats up. And that heat, that rising temperature, it ignites a shell of hydrogen around the core, hydrogen that wasn't hot enough to fuse before. So now you have this strange situation where the core is contracting and heating up, but the outer layers of the star are expanding, cooling, turning red. The star becomes what we call a red giant. And when the sun becomes a red giant, it's going to swell up enormously. I mean enormously. It's going to expand beyond the orbit of Mercury, probably beyond Venus, maybe even to where Earth is now. The exact details depend on complicated physics we don't fully understand, but the basic picture is clear. The sun is going to balloon outward, turning into this huge, bloated red star. And Earth, if it survives at all, is going to be a charred, lifeless rock, maybe even consumed entirely by the expanding sun. That's the fate of our planet, of our star, of our solar system. But that's just one star, one death among countless trillions. Now, while the sun is in this red giant phase, something interesting is happening in the core. It's still contracting, still heating up, and eventually it gets hot enough to start fusing helium. You see, helium is harder to fuse than hydrogen. It requires higher temperatures, more energy, more pressure. But if the core gets hot enough, if it reaches about 100 million degrees, then helium atoms can start fusing together to form carbon and oxygen. And when this happens, when helium fusion begins, the star stabilizes again for a while. It's found a new source of fuel, a new way to balance gravity. But here's the thing. Helium doesn't last as long as hydrogen. There's less of it, and it burns faster. So this phase, this helium burning phase, it's much shorter. For the sun, it'll last maybe 100 million years. And then the helium runs out too. And when the helium runs out, well, for a star like the sun, that's basically it. The core isn't massive enough, isn't hot enough to fuse carbon and oxygen into heavier elements. It just can't get there. So what happens is the core collapses one final time, and the outer layers of the star, these huge bloated layers, they get blown away. They just drift off into space, forming what we call a planetary nebula, one of those beautiful, colorful clouds you see in space photos. And what's left behind, what remains at the center, is this tiny, incredibly dense object called a white dwarf. It's about the size of Earth, but with about half the mass of the sun packed into that small volume. And it's hot, incredibly hot, but it's not fusing anything anymore. It's not generating new energy. It's just sitting there slowly cooling off, radiating away the heat from its past life as a star. And a white dwarf, it's going to cool for a very long time, billions upon billions of years. Eventually, after so long that the time scale is hard to even comprehend, it'll cool enough that it stops glowing at all. It becomes what's called a black dwarf, a cold, dark, dead lump of carbon and oxygen floating through space. And as far as we know, the universe isn't old enough yet for any black dwarfs to exist. The oldest white dwarfs are still glowing, still hot. But they will cool eventually. They have to. That's just thermodynamics. And when they do, when all the white dwarfs in the universe have finally cooled to the background temperature of space, well, that's one way the stars disappear. They don't explode or collapse into black holes. They just fade away, cooling ember by cooling ember, until there's nothing left to see. But that's just medium-sized stars, massive stars, stars much bigger than the sun. They die in a very different way. They die violently. You see, when a massive star runs out of hydrogen, it becomes a red supergiant, similar to how the sun becomes a red giant, but much, much larger. And then it starts fusing helium, just like the sun will. But here's where it gets different. When a massive star runs out of helium, it's got enough mass enough gravitational pressure that its core can get hot enough to fuse carbon. And then when the carbon runs out, it can fuse neon, and then oxygen, and then silicon. Each stage producing heavier and heavier elements, each stage lasting shorter and shorter periods of time. And you end up with this bizarre onion-like structure inside the star. At the very center, you have an iron core. Surrounding that, a shell fusing silicon into iron. Surrounding that, a shell fusing oxygen, then neon, then carbon, then helium, then hydrogen. All these layers burning at once, each one producing the fuel for the next. And this whole process, from when the star starts fusing carbon to when it develops an iron core, it might take only a few thousand years, maybe less. It's incredibly fast by stellar standards. And then comes the moment of catastrophe, because iron is special. Iron is the most stable nucleus. Fusing iron doesn't release energy. It actually requires energy. So when the core turns to iron, when there's nothing left but iron in the center of the star, fusion stops completely, suddenly. And without fusion, there's nothing to hold up the core against gravity, nothing at all. And the core collapses. And I don't mean it contracts slowly. I mean it collapses catastrophically in less than a second. The core of a star, something with a mass greater than the sun's, something bigger than Earth, it collapses down to a sphere maybe 20 kilometers across. 20 kilometers in less than a second. And when that happens, when the core collapses that fast, the infalling matter slams into the incredibly dense core and bounces. It rebounds. And that rebound, that shockwave, it blasts outward through the star, blowing the entire thing apart. This is a supernova, one of the most energetic events in the universe. For a brief time, a few weeks, a single exploding star can shine as brightly as an entire galaxy, billions of stars worth of light coming from one dying star. And when it's over, when the explosion fades, what's left is either a neutron star or a black hole, depending on how massive the core was. A neutron star is it's even denser than a white dwarf. It's made entirely of neutrons packed together so tightly that a teaspoon of neutron star material would weigh 1 billion tons. 1 billion tons in a teaspoon, and it's tiny, just 10 or 20 kilometers across, but spinning incredibly fast, sometimes hundreds of times per second, and with a magnetic field trillions of times stronger than Earth's. And like a white dwarf, a neutron star doesn't fuse anything. It's just sitting there, slowly cooling, slowly spinning down, slowly fading. It'll last for an incomprehensibly long time, but eventually it too will cool completely. It too will become invisible. Or if the core is massive enough, if it's more than about 2 or 3 times the sun's mass, then even neutron degeneracy pressure can't stop the collapse, and the core just keeps collapsing, keeps crushing down until it forms a black hole, a region of space-time so curved, so warped by gravity that nothing can escape from it, not even light. And black holes, well, they're a different kind of death. They don't cool and fade like white dwarfs and neutron stars. They just sit there, swallowing anything that gets too close, growing slowly as they feed. But even black holes aren't forever. Even they will eventually disappear, though we'll get to that later. So that's how individual stars die. Medium-sized stars become white dwarfs. Massive stars explode as supernovae and become neutron stars or black holes. But here's the thing, here's what really matters when we're talking about the disappearance of stars. Stars aren't just dying. New stars are also being born. Right now, all across the universe, in clouds of gas and dust, new stars are forming. Gravity pulls the gas together, the cloud collapses, the center heats up, fusion begins, and a new star is born. And this has been happening for billions of years. It's been happening since very early in the universe's history, since just a few 100 million years after the Big Bang. So you might think, okay, stars die, but new stars are born. Maybe it balances out. Maybe the universe stays full of stars forever. But it doesn't balance out. It can't, because there's a fundamental problem, a fundamental limit. You see, when a star forms, it's forming from hydrogen and helium, the primordial elements left over from the Big Bang. And when a star dies, some of that hydrogen and helium gets locked up in remnants, in white dwarfs, neutron stars, black holes. Some of it gets blown back out into space, enriched with heavier elements forged in the star's core and in supernova explosions. And that enriched gas can form new stars. But each generation, each cycle of star formation and death, more and more material gets locked up in stellar remnants. More and more hydrogen and helium becomes unavailable for making new stars. And the clouds of gas that do remain, they're getting more and more enriched with heavy elements, which changes how efficiently they can collapse to form stars. And this means that star formation is declining. It's been declining for billions of years already. The universe is making fewer new stars now than it did in the past. And this trend, it's going to continue. Eventually, in the far future, the universe is going to run out of gas to make new stars. All the available hydrogen will either be in stars, in stellar remnants, or spread so thin across the expanding universe that gravity can't pull it together anymore. And when that happens, when the last new star forms, when the era of star formation comes to an end, then it's just a matter of time. The stars that exist will burn out one by one, and no new stars will replace them. Now, when does this happen? When does star formation end? Well, that depends on a lot of complicated astrophysics, but the best estimates suggest that we're already past the peak. The universe made stars most efficiently about 10 billion years ago, when it was a few billion years old. We're living about 14 billion years after the Big Bang, and star formation has already declined to a fraction of what it used to be, and it's going to keep declining. In another trillion years, most of the gas will be used up. Star formation will drop to almost nothing. There might be a few last stragglers, a few final stars born from the dregs of remaining gas, but by and large, the era of making new stars will be over. The universe will have used up its fuel, its raw material, and from that point on, it's all downhill. It's all just waiting for the existing stars to burn out, and the timescale on which they burn out, well, it varies enormously. Massive stars, the big bright ones, they burn out fast. Some of them only last a few million years, but low-mass stars, red dwarfs, they burn incredibly slowly. A red dwarf with about 10% of the sun's mass can last for 10 trillion years. 10 trillion, that's about 700 times the current age of the universe. These tiny, dim stars, barely visible even with telescopes, they're going to be the last stars shining in the cosmos. Long after the sun has died, long after all the bright stars you can see with your naked eye have burned out, red dwarfs will still be glowing, still fusing hydrogen, still keeping a faint light burning in an increasingly dark universe. And this is where things get really strange, where the timescales become almost incomprehensible, because we're not talking about millions of years or billions of years anymore. We're talking about trillions, quadrillions. Timescales so long that the entire history of the universe so far, 14 billion years, is like a split second in comparison. And on these timescales, even red dwarfs will eventually burn out. Even they will run out of hydrogen, swell up briefly in their own tiny version of a red giant phase, blow off their outer layers, and leave behind a white dwarf. And when the last red dwarf becomes a white dwarf, probably something like 100 trillion years from now, that's it. That's the end of the stelliferous era, the age of stars. No more stars will be forming. No more stars will be burning. The universe will be filled with stellar remnants, white dwarfs, neutron stars, black holes, planets, asteroids, all of it cold, dark, dead. But even then, even after the stars have gone out, the universe isn't finished changing. It's just entering a new era, what cosmologists call the degenerate era. And in this era, the dominant objects in the universe are degenerate matter objects, white dwarfs and brown dwarfs. Brown dwarfs are these failed stars, objects that weren't quite massive enough to start fusing hydrogen, just sitting there slowly cooling from their formation heat. And white dwarfs, as we discussed, cooling from their past lives as stars. And these objects, they're going to cool for an unimaginably long time. The universe right now has a background temperature, the cosmic microwave background, left over from the Big Bang. It's about 3 degrees above absolute zero. And as the universe expands, this background temperature is dropping. It's getting colder. Eventually, in the deep future, the background temperature will be so low, so close to absolute zero, that white dwarfs and brown dwarfs will cool to match it. They'll reach thermal equilibrium with the universe itself. And when that happens, they'll be completely invisible. They won't emit any radiation at all, or at least nothing detectable. They'll just be cold, dark lumps of matter, floating through an even colder, even darker universe. But here's where it gets interesting, where quantum mechanics enters the picture. Because even in this cold, dark era, things are still happening. Very slowly, on timescales that make even 100 trillion years look short, but still happening. You see, matter isn't perfectly stable. Protons, the building blocks of atoms, we think they might decay. We're not certain about this, we've never observed it directly. But many theories in particle physics predict that protons have a finite lifetime. Maybe 10 to the 34th power years, maybe 10 to the 36th power years, maybe longer. But if they do decay, if protons aren't absolutely stable, then eventually every white dwarf, every brown dwarf, every planet, every rock, they're all going to slowly dissolve. The protons that make up their atoms will decay into lighter particles, into radiation, and the matter will just dissipate. And if proton decay happens, the degenerate era will eventually give way to the black hole era. Because by this time, after 10 to the 40 years or so, the only large-scale structures left in the universe will be black holes. Everything else will have decayed away, evaporated, dispersed, and the universe will be almost empty. Just black holes scattered across an expanding, cooling space with nothing else around them. No stars, no planets, no gas, no dust. Just black holes, and you might think, well, black holes last forever, right? They don't evaporate, they don't decay, they're eternal, except they're not. And this is where Stephen Hawking made one of the most profound discoveries in theoretical physics. In the 1970s, Hawking showed that black holes actually do evaporate. Slowly, incredibly slowly, but they evaporate. And the reason has to do with quantum mechanics and the nature of vacuum. You see, the vacuum, empty space, isn't really empty. It's filled with quantum fluctuations, virtual particles popping in and out of existence. And near the event horizon of a black hole, these fluctuations can do something remarkable. A pair of virtual particles, a particle and an antiparticle, can be created right at the horizon, and one of them can fall into the black hole while the other escapes. And from the outside, it looks like the black hole has emitted a particle. It's radiating. And this radiation, this Hawking radiation, it carries energy away from the black hole, which means the black hole is losing mass. It's evaporating. Now, for a large black hole, a stellar mass black hole or a supermassive black hole at the center of a galaxy, the rate of evaporation is incredibly slow, unimaginably slow. A black hole with the mass of the sun would take about 10 to the 67th power years to evaporate completely. That's 10,000 trillion years. And a supermassive black hole, one with billions of times the sun's mass, would take even longer, maybe 10 to the power of 100 years or more, but eventually, inevitably, they'll all evaporate. Hawking radiation will slowly chip away at them until there's nothing left. And when the last black hole evaporates, when it finally gives up its mass in a burst of radiation, that's the end of the black hole era. And what comes after that? What comes after even the black holes are gone? Well, that's what cosmologists call the dark era. And it's dark not just because there are no stars, not just because there's no light. It's dark because there's almost nothing left. Just photons, particles of light stretched out by the expansion of the universe to wavelengths longer than galaxies. Just electrons and positrons, the decay products of all that matter that used to exist. Just neutrinos, ghostly particles that barely interact with anything. All of it spread so thin across space that you might travel for trillions of light years and never encounter a single particle. The universe at this point is basically empty. It's cold, it's dark, it's expanding, and there's nothing happening. No stars, no galaxies, no black holes, no structures. Just a thin soup of elementary particles getting more and more dilute as space expands, approaching a state of maximum entropy, maximum disorder, what we call heat death. And entropy, that's really the key to understanding all of this. Entropy is it's a measure of disorder, of randomness, of how spread out and mixed up things are. And the second law of thermodynamics says that entropy always increases in a closed system. It never decreases. Things always tend toward disorder, toward equilibrium, toward uniformity. And stars are highly ordered structures. They're concentrations of matter and energy, burning hydrogen, producing light, creating gradients of temperature and density. They're fighting against entropy temporarily. but they can't win. Not in the long run. Eventually, the hydrogen runs out, the star dies, and the energy it produced gets spread out, radiated away, diluted across space. And with each star that dies, the entropy of the universe increases. It becomes a little more disordered, a little more uniform, a little closer to heat death. And the expansion of the universe is helping this along, because as space expands, everything gets more spread out. Matter gets more dilute, temperature drops, energy gets redshifted to longer and longer wavelengths, lower and lower frequencies. And the universe is heading toward a state where everything is at the same temperature, the same density, the same level of disorder everywhere. There are no gradients, no differences, no structures. And in such a state, nothing can happen. No work can be done. No complexity can exist. It's the ultimate end, the final equilibrium. Heat death. Now, there are some uncertainties in this picture. There are things we don't fully understand. We don't know for sure if protons decay. We don't know the exact properties of dark energy, the mysterious force driving the universe's accelerating expansion. We don't know if there are other physical processes, other phenomena that might become important on these extreme timescales. Maybe there are. Maybe there's something we're missing, some mechanism that could change the story. But based on what we do know, based on our current understanding of physics, this is where the universe is headed. Stars will die one by one. No new stars will form. Stellar remnants will cool and decay. Black holes will evaporate. And the universe will end up cold, dark, empty, and essentially dead. And the timescales involved, they're so vast that they're almost meaningless to human minds. I mean, how do you comprehend 10 to the 100 years? How do you even think about a number that large? The universe is 14 billion years old. Written out, that's 14 billion years. Now write out 10 to the power of 100 years. That's a 1 followed by 100 zeros. 100 quadrillion years. And that's not even the end of the timescales cosmologists talk about. Some processes might take 10 to the power of 1,000 years, or 10 to the power of 10 to the power of 76 years. Numbers so large that just writing them out would require more atoms than exist in the observable universe. But here's the thing, here's what I find both unsettling and oddly beautiful about all this. We can know about these timescales. We can calculate them, predict them, understand them, even though they're so far beyond human experience that they might as well be infinite. We can trace the future history of the universe from where we are now, in this bright, star-filled era, through the decline of star formation, through the death of the last stars, through the cooling of white dwarfs, through the evaporation of black holes, all the way to heat death. We can see the whole arc of cosmic history from beginning to end, even though we'll only ever experience the tiniest fraction of it. And there's something profound about that, something deeply moving, because we're not just living in a universe, we're living in a universe that has a story, a narrative, a trajectory. It began in a hot, dense state 14 billion years ago. It's been expanding, cooling, evolving ever since. It formed stars and galaxies and planets and eventually life and consciousness. And it's going to continue evolving, continue changing until it reaches a state so different from now that we can barely imagine it. A state where all the stars have died, where all the light has faded, where the universe is dark and cold and still. And we're here right now in the middle of that story. We're living in the age of stars, the brief, brilliant era when the universe is actually bright. Because that's what this is, right? This is the golden age, the stelliferous era, the age when stars fill the cosmos, when galaxies shine, when you can look up at night and see a sky full of light. And it's not going to last. It's already in decline. We're past the peak. And in the deep future, in timescales we can't even really comprehend, it'll all be gone. The stars will go out one by one until there are none left, and the universe will be dark. And I think there's something both terrifying and strangely comforting about that. Terrifying because it means everything ends. Everything. Not just us, not just humanity or life on Earth, but everything. Every star, every galaxy, every structure in the entire universe. All of it temporary. All of it doomed to fade and die. But comforting too, in a way, because it puts things in perspective. All our worries, all our struggles, they're happening in this tiny sliver of time, this brief moment in cosmic history when stars exist at all. We're not witnessing eternity. We're witnessing a phase, an era, a temporary condition. And maybe there's a kind of freedom in that. Maybe it means we should appreciate what we have while we have it. The light, the warmth, the complexity, the life. But let me back up a bit because I want to talk more about what stars actually mean for the universe, for complexity, for existence itself. Because stars aren't just pretty lights in the sky. They're not just interesting astrophysical objects. They're engines of complexity. They're the reason anything interesting exists at all. You see, when the universe began, in the first moments after the Big Bang, it was almost entirely hydrogen and helium, the simplest elements. And that was it. Just hydrogen and helium with tiny traces of lithium, nothing else. No carbon, no oxygen, no iron, none of the elements that make up planets or oceans or living things. Those elements, all of them, they were forged inside stars. When a star fuses hydrogen into helium, and then helium into carbon, and then carbon into oxygen, it's creating new elements. It's taking simple matter and making it complex. And when a massive star explodes as a supernova, the extreme conditions in that explosion can create even heavier elements. Gold, uranium, thorium, all the elements heavier than iron, they're made in supernovae and in the collisions of neutron stars. And then those elements get scattered into space, mixed into clouds of gas and incorporated into the next generation of stars and planets. Every atom in your body, heavier than hydrogen, every bit of carbon, every bit of oxygen, every bit of iron in your blood, it was made inside a star. You are literally made of stardust. We all are, and so is the Earth, and so is everything around you. And this means that stars are essential for complexity. Without stars, the universe would just be hydrogen and helium forever. There would be no planets, no chemistry, no biology, no life, no consciousness, nothing even remotely interesting. Stars are the crucibles where the universe becomes interesting, where simple matter transforms into complex matter, where the building blocks of everything we care about are forged. And when the stars die, when they all burn out and no new stars form, that process stops. No new elements are being made. No new complexity is being created. The universe is just coasting on the elements that already exist, slowly degrading, slowly decaying, slowly running down. And that's what entropy is really about, in a way. It's not just about disorder in an abstract sense. It's about the loss of gradients, the loss of differences, the loss of the ability to do things. When you have a hot star and a cold background, you have a temperature gradient. And gradients can drive processes. They can power things. They can create complexity. But when everything is the same temperature, when everything is in equilibrium, there are no gradients. And without gradients, nothing can happen. The universe becomes static, frozen not in ice, but in uniformity. And stars, for all their violence, for all their heat and fury, they're creating gradients. They're pumping energy into the universe, creating differences, enabling things to happen. And when they're gone, when the last star burns out, the universe will still exist, but it'll be a much less interesting place, a much less active place, a much less alive place. And that brings up another question, another layer to this. What about life? What about consciousness? I mean, we exist now during the age of stars, and that's not a coincidence. We need stars. We need the sun specifically. It provides the energy that drives photosynthesis, that warms the planet, that makes life possible. And in the far future, when the sun dies, life on Earth dies too. There's no avoiding that. But what about life elsewhere? What about civilizations that might exist around other stars, around those long-lived red dwarfs that will still be burning trillions of years from now? Could they survive? Could they adapt? Could they keep existing even as the universe grows darker and colder? And the answer is maybe, for a while, red dwarfs will still be shining long after the sun is gone. Any planets around them, if they're in the right orbit, if they have the right conditions, they could potentially harbor life for trillions of years. But eventually, even those stars will die. And when they do, any life that depends on them will face a crisis. They'll need to find a new energy source. And in a universe where stars are dying out, where no new stars are forming, energy becomes increasingly scarce. There are no easy solutions. Maybe a sufficiently advanced civilization could somehow tap into the rotational energy of black holes, or the energy stored in the structure of matter itself, or something else we haven't even thought of. But it's hard to see how life, at least life as we understand it, could persist indefinitely in a universe heading toward heat death. And that's a sobering thought, isn't it? That not only will the stars die, But life itself, all life, everywhere, is probably doomed. Maybe not on timescales we need to worry about. Maybe not for trillions of years. But eventually, probably inevitably, life will end. The universe will become too cold, too dark, too empty to support any kind of complexity, including living things. And there's something deeply sad about that. The idea that the universe, for all its vastness, for all its beauty, is fundamentally inhospitable to life in the long run. That life is just a temporary fluke, a brief anomaly in a cosmos heading toward eternal darkness and silence. But maybe that's the wrong way to think about it. Maybe the fact that life exists at all, even temporarily, even in this brief window of cosmic history, when stars shine and planets exist and complexity is possible, maybe that's the miracle. Maybe we shouldn't be sad that it ends. Maybe we should be grateful that it happens at all, because it didn't have to. There's nothing in the laws of physics that requires life to exist. The universe could have been just hydrogen and helium, expanding and cooling forever. But instead it made stars, and stars made heavy elements, and heavy elements made planets. And somewhere along the way, on at least one of those planets, maybe on many of them, matter organized itself into something that could think, that could wonder, that could look up at the stars and ask questions. And that's extraordinary, that's beautiful, even if it's temporary. And there's another angle to this, another way of thinking about the death of stars that I find fascinating. It has to do with time itself, with our perception of time, with what it means for something to last forever. Because here's the thing, when we say the stars will die, we're speaking from our perspective, from the perspective of human beings living in a particular era of cosmic history. But time, time is weird. Einstein taught us that. Time is relative. It depends on your frame of reference, on how you're moving, on how strong the gravitational field is around you, and on cosmic scales, when you're dealing with billions and trillions and googles of years, the very concept of time starts to break down in strange ways. For example, from the perspective of a photon, a particle of light, time doesn't pass at all. Photons travel at the speed of light, and at that speed, time dilation becomes infinite. From the photon's perspective, it's created and absorbed in the same instant, even if billions of years pass in the reference frame of everything else. And black holes, they warp space-time so severely that time behaves in incredibly counterintuitive ways. An object falling into a black hole from its own perspective falls in a finite amount of time. But from the perspective of an outside observer, it never quite reaches the event horizon. It just gets slower and slower, redder and redder, fainter and fainter, or asymptotically approaching the horizon, but never crossing it. And in the far future, in the deep cosmological future, time itself becomes meaningless in some sense. When the universe has reached heat death, when everything is in thermal equilibrium, when nothing is changing anymore, how do you even measure time? Time, in a practical sense, is measured by change, the ticking of a clock, the burning of a candle, the beating of a heart, the decay of a radioactive nucleus. But if nothing changes, if there are no processes, no events, no dynamics, then in what sense does time still exist? Maybe it does in some abstract mathematical sense as a coordinate in space-time. But experientially, phenomenologically, time requires change. And in a universe with no stars, no structures, no gradients, no processes, time becomes a meaningless abstraction. So when we say the stars will disappear, we're saying it from our perspective, from the perspective of beings who experience time in a particular way, who exist during a particular era. And that's valid, that's meaningful, but it's also limited. The universe doesn't care about our perspective. It doesn't have a perspective. It just evolves according to physical law, and those laws drive it from one state to another, from hot to cold, from ordered to disordered, from bright to dark. And somewhere in that vast trajectory, in that unimaginable span of time, there's a tiny window where stars exist, and we're in it. Now, I want to talk about dark energy for a moment because it's relevant to how this all plays out. Dark energy is this mysterious thing that makes up about 70% of the universe's energy density. We don't really know what it is. We just know it's there because we can see its effects. And the main effect is that it's causing the expansion of the universe to accelerate. Galaxies aren't just moving apart from each other. They're moving apart faster and faster as time goes on. And this acceleration, it has profound implications for the far future. You see, if the universe were just coasting, just expanding at a constant rate or slowing down, then even as it cooled and spread out, structures would still be gravitationally bound to each other. Galaxies would still be galaxies. Galaxy clusters would still be galaxy clusters. And even in the deep future, even after the stars had died, those structures would persist. But dark energy changes that, because dark energy doesn't dilute as the universe expands. Unlike matter and radiation, which get more spread out as space grows, dark energy stays constant, or at least that's what the simplest models suggest. And if dark energy stays constant while matter and radiation dilute away, then dark energy will come to dominate everything. It already dominates on large scales, but over time, its dominance will increase. And what that means is that the universe's expansion will keep accelerating. And eventually, it'll accelerate so much that even bound structures start to get torn apart. First, galaxy clusters will disperse. Then, maybe galaxies themselves will start to spread out. And in the truly deep future, tens or hundreds of trillions of years from now, even solar systems might get pulled apart by the expansion of space if the acceleration continues. Now, this depends on the exact properties of dark energy, which we don't fully understand. If dark energy is what's called a cosmological constant, a truly constant energy density, then bound structures like solar systems and planets should be safe. They're held together by forces much stronger than the expansion of space. But if dark energy is something else, something that can strengthen over time, then who knows? We might be heading toward a big rip, a scenario where the expansion accelerates so much that everything gets torn apart down to the atoms. But even if we avoid a big rip, even if dark energy is well behaved, it still means the universe is going to become incredibly lonely, because as space expands, galaxies move apart, and eventually they move so far apart that light from one galaxy can't even reach another. The expansion of space, the recession velocity, becomes faster than the speed of light on large enough scales. And this creates what's called a cosmic horizon. Beyond that horizon, you can't see anything. Light from beyond the horizon can never reach you because space is expanding too fast. And over time, that horizon shrinks, in a sense. More and more galaxies disappear beyond it. If there are any civilizations around in the far future, if there are any observers left when the stars are dying, they'll see fewer and fewer galaxies in their sky. Eventually, their galaxy will be the only galaxy they can see. Everything else will have receded beyond the horizon, lost to the accelerating expansion of space. And their galaxy, too, will be dying, its stars burning out, no new stars forming. And eventually they'll be alone in a dark, empty, cold universe. It's a bleak picture, isn't it? The ultimate fate of the cosmos, at least based on what we currently know, is isolation, darkness, cold and death. Everything separated, everything cold, everything still, heat, death, but with the added loneliness of cosmic horizons isolating whatever might remain. And there's no escape from it, at least not that we know of. You can't reverse entropy, you can't make the universe stop expanding, you can't bring the stars back once they've burned out. The laws of physics, as we understand them, are unambiguous. This is where we're headed. But, and I think this is important, but we don't know everything. Physics is not complete. Our understanding of the universe is not final. We're missing things, big things. We don't know what dark energy is. We don't know if protons decay. We don't know what happens to information that falls into black holes. We don't have a complete theory of quantum gravity. We don't understand the initial conditions of the Big Bang. There are gaps in our knowledge, places where new discoveries could change the picture. Maybe there's something, some physical process or phenomenon or symmetry that we haven't discovered yet that becomes important on these extreme timescales. Maybe the far future of the universe is weirder than we imagine. Maybe there are ways for complexity to persist, for life to adapt, for something interesting to happen even in a cold, dark universe, or maybe not. Maybe the picture we have now is basically correct. Maybe the universe really is headed for heat death, for eternal darkness, for the end of everything interesting. We don't know. And we might never know, because these timescales are so far beyond anything we can directly observe or experiment with. We can make calculations, extrapolate our theories, make predictions, but we can't test them. We can't see the future. All we can do is reason from what we know and acknowledge the limits of our knowledge. And in a way, that uncertainty, that not knowing, it's part of what makes this so fascinating, because we're contemplating the ultimate fate of everything, the end of the universe itself, and we don't really know how it's going to go. We have ideas, we have models, but they're based on current physics, and current physics might not be the whole story. So when I say the stars will disappear, I'm saying it with the understanding that this is our best current prediction, based on what we know, but also with the humility to admit that we might be wrong. There might be surprises. The universe has surprised us before. It'll probably surprise us again. And that brings me to another thought, another layer of this. The fact that we can even ask these questions, that we can think about the far future of the universe, that we can trace the life and death of stars across trillions of years. It's remarkable. We're these tiny, fragile creatures living for a few decades on a small planet orbiting an ordinary star in an ordinary galaxy. And yet we can understand, at least in broad strokes, the history and fate of the entire cosmos. We can look back to the Big Bang 14 billion years ago. We can look forward to heat death, maybe 100 to the power of 100 years in the future. We can comprehend timescales and distances and energies so vastly beyond human experience that they might as well be infinite, and yet we can describe them, calculate them, reason about them. That's the power of science, of mathematics, of human thought. We can transcend our limitations, our tiny perspective, and glimpse the big picture. We can see ourselves as we really are, as part of a vast, ancient, evolving cosmos, here for a moment and then gone, but aware, conscious, able to wonder and question and understand. And maybe that's enough. Maybe the fact that the universe can produce beings capable of contemplating its own fate, even if those beings are temporary, even if they're doomed, maybe that's a kind of victory. A triumph of complexity and order over entropy, even if it's just a temporary triumph. There's a concept in philosophy called the absurd, the idea that humans crave meaning and purpose and permanence in a universe that offers none of those things. We want to matter. We want to last. We want our lives, our achievements, our civilizations to mean something, to endure. But the universe doesn't care. It's indifferent. It operates according to impersonal laws, and those laws don't include a provision for meaning or purpose. Stars burn and die. Life arises and ends. Civilizations rise and fall, and eventually everything fades into darkness and cold. And there's no grand plan, no ultimate purpose, no cosmic justice. It just is what it is. And that can feel depressing, it can feel nihilistic. If nothing lasts, if everything ends, if the universe itself is temporary and doomed, then what's the point? Why do anything? Why care about anything? And I think that's a real question, a legitimate philosophical challenge. But I also think the answer, or at least an answer, is that meaning isn't something the universe gives us. It's something we create. We're the ones who assign value, who decide what matters, who choose to care about things even knowing they're temporary. And maybe that's more profound than if meaning were just built into the universe, because it means we're active participants. We're not just following a script, we're writing our own stories, even if those stories take place in a universe that will eventually forget them. And the death of the stars, the eventual darkness and cold, that doesn't negate what happens now. It doesn't make the beauty of a sunset less beautiful, or the love between people less real, or the pursuit of knowledge less worthwhile. Those things matter because we decide they matter. And they matter now, in this moment, in this brief era when stars shine and life exists and consciousness can contemplate the cosmos. The fact that it ends doesn't mean it was meaningless. If anything, maybe the fact that it's temporary makes it more precious, more urgent, more worth cherishing. Because think about it, if the universe lasted forever, if stars burned eternally, if there were no end, no heat death, no darkness, would we appreciate it as much? Would we feel the same sense of wonder at a night sky full of stars if we knew it would always be that way, unchanging, forever? Maybe we would, but maybe the knowledge that it's temporary, that this is a special time, a golden age that won't last, maybe that adds a dimension of poignancy, of beauty, that eternal existence wouldn't have. We're living in a universe that's alive, that's dynamic, that's creating and destroying and evolving. And yes, it's evolving toward darkness and cold. But right now, right here, it's bright. and maybe that's enough. I keep coming back to this idea of timescales because I think it's crucial for understanding not just the science of stellar death, but the philosophy of it. The sun will die in 5 billion years. That's a long time. It's longer than life has existed on Earth. It's longer than the Earth has had continents. It's a timescale so vast that it's almost comforting because it means we don't need to worry about it, not in any practical sense. Humanity, if we survive at all, will have evolved into something unrecognizable long before the sun dies. We'll either have spread to other stars, or will have gone extinct, or will have transformed into something we can't even imagine. The death of the sun is not our problem. It's a problem for our distant descendants if they exist. But when you zoom out, when you look at the death of all the stars, the end of the stelliferous era, then the timescales become so large that they lose all human relevance. 100 trillion years, 10 to the power of 100 years. These are numbers that don't mean anything to human minds. We can write them down, we can calculate with them, but we can't feel them, we can't internalize them. And in a way, that's liberating, because it means this isn't something we need to worry about at all. Not us, not our descendants, not any biological organism, or even any conceivable technological civilization. By the time the stars are truly dying out, by the time the universe is becoming dark, everything we know, everything we care about, will have been gone for so long that it's not even a memory. It's not even a footnote in the history of the cosmos. It's just gone. And yet, we can know about it. We can understand it. We can trace the trajectory. We're living at the beginning of cosmic history, really. The universe is only 14 billion years old. It's a baby. It's going to last for vastly longer than it already has. And we're here, at the start, watching the story unfold, even though we'll only see the tiniest fraction of it. And there's something both humbling and exhilarating about that. Humbling because it shows how small we are, how brief our existence is, how little we matter in the grand scheme. But exhilarating because we can understand it. We're not just passive participants, we're observers who can comprehend the whole arc from beginning to end, even though we only exist for an instant. Let me talk a bit more about what happens to specific things, to planets and galaxies and structures as the stars die. Because it's not just the stars themselves that disappear, it's everything connected to them. Take the Earth, for example. The Earth is about 4.5 billion years old. It formed from the same cloud of gas and dust that formed the sun, a cloud enriched with heavy elements from previous generations of stars. And it's been a dynamic place ever since. Oceans, continents, life, all of it constantly changing, evolving, driven by energy from the sun and from the Earth's own interior. But in 5 billion years, when the sun becomes a red giant, the Earth's story ends. Maybe it gets consumed by the expanding sun. Maybe it survives as a charred, airless rock. Either way, it's dead. No life, no water, no atmosphere. Just a dead world orbiting a dying star. And then, when the sun sheds its outer layers and becomes a white dwarf, Earth, if it still exists, will orbit that white dwarf. It'll be cold. The white dwarf will glow, but not brightly enough to warm a planet at Earth's distance. And over billions of years, the white dwarf will cool. It'll dim, and eventually it'll become a black dwarf, completely dark, completely cold. And Earth, still orbiting, will be a frozen, dead rock circling a frozen, dead star. And that's assuming Earth is even still there. Over billions of years, gravitational interactions with other planets, with passing stars, with the general chaos of orbital mechanics, might destabilize Earth's orbit. It might get flung out into interstellar space, a rogue planet, drifting forever through the dark, or it might spiral inward, eventually colliding with the white dwarf or getting torn apart by tidal forces. And this is the fate of all planets, all of them. Every world, every rock, every ball of gas circling a star, they're all tied to the fate of their stars. When the star dies, the planetary system dies with it. Maybe some planets get ejected and survive as rogue planets, drifting through space, but they're lifeless, frozen, dark, and even those won't last forever. Over enormous timescales, they'll either get swallowed by black holes, or they'll decay as their constituent protons decay, or they'll get torn apart by tidal forces from passing objects. Eventually, there will be no planets, just like there will be no stars, and galaxies too will change. Right now, galaxies are these vast collections of stars hundreds of billions of them, held together by gravity, rotating, evolving, colliding with each other sometimes and merging. And they're bright. You can see nearby galaxies with a good telescope, and they're full of stars, full of light. But in the far future, as star formation ends, galaxies will go dark. They'll still exist for a while as collections of stellar remnants, white dwarfs, neutron stars, black holes, all orbiting the supermassive black hole at the galaxy's center. But they won't shine. They'll be dark galaxies, invisible except for the gravitational effects they have on anything nearby. And even those dark galaxies won't last. Over trillions of years, gravitational interactions between the remnants will cause some of them to gain energy and get flung out of the galaxy entirely, while others lose energy and spiral inward toward the central black hole. It's a process called evaporation, and it's analogous to how molecules in a gas can escape if they gain enough energy. And eventually, the galaxy evaporates. Most of its mass gets flung out into intergalactic space, and the rest falls into the central black hole. And then the black hole itself, over vastly longer timescales, evaporates via Hawking radiation. And then there's nothing left. No galaxy, no stars, no remnants, just empty space, slightly warmer than it was before because the black hole's evaporation released some energy, but basically empty. And this will happen to all galaxies. The Milky Way, Andromeda, all the galaxies in the observable universe, they'll all evaporate or merge with each other and then evaporate. And in the end, there will be no galaxies, no structures, just a thin, expanding, cooling soup of particles and radiation approaching heat death. And that's it. That's the end of the story. The universe started with a bang, the Big Bang, this incredibly hot, dense, energetic state. And it's going to end with a whimper, with cold, darkness, silence, stillness, heat death, the big freeze, the ultimate triumph of entropy. Unless there's something we don't know, some new physics, some loophole, some way for the universe to surprise us one more time. And I think it's important to acknowledge that possibility, even if it seems unlikely, because science is always provisional. It's always open to revision. We've been wrong before. We thought the universe was static, eternal, unchanging. Then we discovered it was expanding. We thought the expansion would slow down. Then we discovered dark energy and learned it was accelerating. We thought black holes destroyed information. Then Hawking and others showed that maybe they don't, that information might be preserved somehow. We keep learning, keep discovering, keep revising our understanding. So maybe the far future of the universe isn't what we think. Maybe protons don't decay. Maybe dark energy changes over time in ways that prevent heat death. Maybe there are quantum fluctuations that can create new universes, new big bangs, even in a seemingly dead cosmos. Maybe consciousness or intelligence finds a way to persist, to extract energy from the structure of space-time itself, to keep going even when there are no stars. Maybe the universe is cyclic, endlessly repeating, with each Big Bang followed by expansion, star formation, heat death, and then somehow another Big Bang. We don't know. We can't know. Not yet. Maybe not ever. But based on what we do know, based on our current best understanding, the stars are going to die. All of them. And no new stars will replace them. And the universe will become dark and cold and empty. And that's a sobering truth, a hard truth, a truth that makes you confront the impermanence of everything. But it's also a truth that gives you perspective, that reminds you of your place in the cosmos, that shows you just how special this moment is, this brief era when stars shine and life exists and the universe is full of light and energy and possibility. You know, there's a quote, I can't remember who said it, but it goes something like this: "We are a way for the universe to know itself." And I think that's beautiful, because that's what we are, right? We're matter, organized in such a way that it can think, can observe, can understand. We're made of atoms forged in stars, and we're using those atoms to study stars, to comprehend them, to figure out their life cycles and their deaths and what it all means. We're the universe looking at itself, and when the stars die, when consciousness ends, if it ends, then the universe will no longer know itself. It'll just be matter and energy, following physical laws, with no one to observe, no one to understand, no one to care. And maybe that's the real tragedy of the death of stars. Not that the stars themselves will be gone, but that the light will be gone. And light, in both the literal and metaphorical sense, is what makes the universe knowable. You can't see in the dark, you can't observe without light, and you can't understand without observation. So when the stars go out, when the universe becomes dark, it also becomes unknowable. It becomes a place where nothing can see, nothing can understand, nothing can wonder. And if there's any consciousness left at that point, any remnant of life or intelligence struggling to survive in the cold and dark, they'll be living in a universe that's fundamentally diminished, a universe that's lost its capacity for complexity, for beauty, for meaning. But we're not there yet. We're here now in the age of stars. And it's an age worth celebrating. Every time you look up at the night sky and see those points of light, you're seeing nuclear furnaces, vast beyond comprehension, burning hydrogen, creating energy, forging the elements that make up everything you know. You're seeing the universe at its most active, its most energetic, its most alive. And it won't last forever, but it's lasting now. And that's something. That's everything, really. So maybe the answer to why the stars will disappear isn't just a scientific answer. It's not just about entropy and fusion and heat death. It's also a philosophical answer. The stars will disappear because nothing lasts forever, because the universe is dynamic, evolving, changing, because the laws of physics drive everything toward equilibrium, towards simplicity, towards stillness. But before that happens, before the darkness and the cold, there's this, there's now, there's light, there's warmth, there's complexity, there's life, there's consciousness, there's us looking up, wondering, understanding. And maybe that's the point. Maybe the journey matters more than the destination. Maybe the fact that the universe can be bright, can be alive, can be aware, even if only for a while, maybe that's enough. Maybe that's the answer. Not to why the stars will disappear, but to why it's okay that they will. Because they existed at all, because we existed to see them, because for a brief, brilliant moment in cosmic history, the universe was full of light and we were there. Now let's move on to another theory for you to reflect on. I've been thinking about time, about the past and the future, and specifically about what it means for them to be infinite, endless, stretching forever in both directions. And it's one of those things that seems like it should be simple, right? The past is what happened before, the future is what comes after, and maybe they just go on forever. But when you really start to dig into it, when you actually try to wrap your mind around what an infinite past or an endless future would mean, that's when things get strange. Because infinity isn't just a really big number, it's something fundamentally different, something that breaks our normal ways of thinking. And the universe doesn't seem to care much about what makes sense to us, what feels comfortable or intuitive. So let's start with something basic, something we all experience every day. You wake up in the morning, right? And you remember yesterday. Maybe you remember what you had for breakfast, what you did at work, who you talked to, and you can remember the day before that and the day before that. Your memories stretch back into the past, getting hazier and less detailed the further back you go, but they're there, at least in some form. And intellectually, that before you were born, there were other days, other years, other centuries. Your parents existed before you, their parents before them, and so on back through human history. Before humans, there were other species, other geological eras, the formation of Earth itself, the birth of the sun, the beginning of the universe. That's the story we tell ourselves. The narrative that feels natural, that time stretches back through this long chain of causes and effects. But here's where it starts to get interesting, where the questions start to pile up. How far back does that chain go? Is there a first moment, a beginning to it all? Or does it just keep going back and back and back forever? And if there is a beginning, what came before that? What was there before the beginning? Those questions sound almost childish, don't they? The kind of thing a kid asks that makes adults uncomfortable because we don't really have good answers. But they're profound questions, questions that have occupied some of the greatest minds in human history, philosophers and theologians and physicists, all trying to grapple with this fundamental mystery about the nature of time itself. And the future, well, that's just as puzzling. You can plan for tomorrow, next week, next year. You can imagine the future, make predictions about what might happen. But does the future already exist in some sense? Is it laid out there, determined, waiting to unfold? Or is it open, undecided, a space of pure possibility? And does it go on forever? Will there always be a tomorrow, and a day after that, and another after that, stretching out into infinity? Or will there be an end? A final moment after which there is no more time? These aren't just abstract philosophical puzzles. These are questions that cut to the heart of what it means to exist, to be a creature that exists in time, that remembers a past and anticipates a future. You see, the thing about infinity is that it's not just really big, it's categorically different from any finite number, no matter how large. If you have 1 billion years, that's a lot of years, an almost incomprehensible amount of time. But it's still finite, still countable in principle. Add one more year and you have 1,000,000,001. You can imagine, at least in theory, counting through all those years. But infinity doesn't work that way. You can't count to infinity. You can't add one to infinity and get a bigger number. Infinity plus 1 billion is still infinity. Infinity times 1 billion is still infinity. It's not a number at all, really. It's more like a concept, a way of saying keeps going without end. And when we try to apply this concept to time, when we try to imagine an infinite past or an infinite future, we run into all sorts of paradoxes and puzzles. Because if the past is infinite, if there's no beginning, then that means an infinite amount of time has already elapsed to get to this moment right now. And how do you get to the present moment? By passing through an infinite number of previous moments. It seems impossible, right? Like you could never finish counting an infinite series of numbers. So how could the universe finish passing through an infinite series of moments to arrive at now? That's what philosophers call the problem of traversing an infinity. And it's troubled thinkers for thousands of years. Aristotle thought about this, back in ancient Greece. He argued that time couldn't have a beginning because if it did, there would have been a first moment. And what would have caused that first moment to come into existence? What would have been there before it to bring it about? But he also struggled with the idea of an infinite past because it seemed to lead to these logical problems. And this tension, this puzzle about whether time has a beginning or goes back forever, it's persisted throughout history, showing up in different forms in different cultures and philosophical traditions. Medieval Christian theologians grappled with it too, trying to reconcile the biblical account of creation with philosophical arguments about time and causation. Augustine had this brilliant insight where he argued that time itself was created along with the universe, that there was no before creation because time didn't exist yet. Asking what came before the beginning of time is like asking what's north of the North Pole. It's a category error, a question that doesn't make sense because it presupposes something that isn't there. And that's a profound idea, right? That time isn't this eternal container that exists independently and within which events happen, but rather that time is part of the universe itself, part of the created order. But then you have other traditions, other ways of thinking about time that are more comfortable with the idea of cycles and eternal recurrence. Ancient Indian philosophy, for instance, with its concept of cosmic cycles, yugas that repeat over vast stretches of time, the universe being created and destroyed and created again in an endless wheel. Or the ancient Stoics in Greece who believed in eternal return, the idea that the universe would eventually return to the same state and repeat the same events over and over infinitely. These cyclical views of time don't have the same problem with traversing an infinity because they're not imagining a linear progression with a beginning and an end. They're imagining something more like a circle where the end loops back to the beginning. Now, this is all philosophy and theology, right? Ways of thinking about time that come from pure reasoning and religious revelation. But what does science tell us? What can we actually observe and measure about the nature of time, about whether the past is infinite or finite, whether the future goes on forever or comes to an end? And this is where things get really fascinating because the scientific story that emerged in the 20th century was revolutionary, completely unexpected, and in many ways even stranger than the philosophical speculations that preceded it. The big breakthrough came with Einstein, of course. Einstein's theory of relativity fundamentally changed how we think about time. Before Einstein, time was thought to be absolute, universal, the same for everyone everywhere. Newton imagined time as flowing uniformly, like a river that carries everything along at the same rate. But Einstein showed that time is relative, that it depends on how fast you're moving and how strong the gravitational field is around you. Time literally runs at different rates in different circumstances. A clock on a fast-moving spaceship runs slower than a clock on Earth. A clock near a massive object like a black hole runs slower than a clock far away from any mass. And this relativity of time has profound implications. It means that time isn't this separate thing that exists independently of space and matter and energy. Time and space are woven together into a single fabric called space-time, and that fabric can be warped and bent by the presence of mass and energy. Gravity isn't a force pulling things together, it's the curvature of space-time itself. Matter tells space-time how to curve, and space-time tells matter how to move. It's this beautiful, elegant, geometric picture of reality. But here's what's really important for our question about infinite past and endless future. Einstein's equations, the field equations of general relativity, they allow us to model the universe as a whole, to treat the entire cosmos as a single physical system evolving over time. And when physicists started doing this in the early 20th century, they discovered something remarkable. The universe isn't static. It's not sitting still in some eternal, unchanging state. It's changing, evolving, and specifically, it's expanding. This was a shocking discovery. Observations by Edwin Hubble in the 1920s showed that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. Space itself is expanding, like the surface of a balloon being inflated, with galaxies embedded in that surface getting farther apart as the balloon grows. And if the universe is expanding now, that means it was smaller in the past. Wind the clock backward, and the universe gets denser and hotter. Keep going back, and you reach a point where all the matter and energy in the universe was compressed into an incredibly tiny, incredibly hot, incredibly dense state. And this is what we call the Big Bang. Now, the Big Bang is probably the most misunderstood concept in all of cosmology, right? People hear Big Bang and they imagine an explosion like a bomb going off in space, matter flying outward from some central point. But that's not what it is at all. The Big Bang wasn't an explosion in space. It was the beginning of space itself, the beginning of time itself. There was no place where it happened because space didn't exist yet. There was no before in the usual sense because time didn't exist yet. The Big Bang is the boundary of space-time, the point beyond which we can't go back, at least not with our current physics. And this is huge, right? This means that the past isn't infinite after all, at least not in the straightforward sense. If the Big Bang happened about 13.8 billion years ago, then that's as far back as time goes. There are only a finite number of moments between now and the beginning. You could, in principle, count them if you had enough time and patience. The problem of traversing an infinity, that philosophical puzzle that troubled Aristotle and medieval scholars, it goes away because there is no infinity to traverse. The past is finite, bounded by this singular beginning point. And here's where it gets tricky. What does it mean to say that time began at the Big Bang? What was there before? Augustine's answer comes back into play, right? Maybe there is no before because time itself came into existence with the Big Bang. Asking what happened before the Big Bang is like asking what's north of the North Pole. It's not that there's some mysterious thing there that we don't know about. It's that the question doesn't make sense within our framework of understanding. Yet physicists aren't completely comfortable with this answer. And I mean, why should they be? It feels unsatisfying, doesn't it, to just say time began without being able to explain how or why or what brought it about. So there have been many attempts to push beyond the Big Bang, to find some more fundamental description of reality that might tell us what, if anything, came before. One idea involves quantum mechanics, that strange theory that describes the behavior of particles and energy at the smallest scales. Quantum mechanics tells us that at tiny distances and short time intervals, reality becomes fuzzy and uncertain. Particles can tunnel through barriers they shouldn't be able to cross. Energy can fluctuate randomly out of nothing, as long as it disappears again quickly enough. The very fabric of space and time becomes subject to quantum uncertainty at scales smaller than about 10 to the power of negative 35 meters and 10 to the power of negative 43 seconds. These are called the Planck length and Planck time, and they represent the limits of our current understanding of physics. At these scales, our classical concepts of space and time break down. We need a theory of quantum gravity, a way of combining Einstein's general relativity with quantum mechanics to describe what happens. And we don't have that theory yet, not fully. String theory is one attempt, loop quantum gravity is another, but neither is complete or experimentally verified. So when we try to talk about the very first instance of the Big Bang, when the entire universe was smaller than the Planck length, we're really speculating, extrapolating beyond what our current physics can handle. Some physicists propose that the Big Bang wasn't really a beginning at all, but rather a transition from some previous state. Maybe there was a pre-Big Bang phase, a different universe or a different configuration of space-time, and what we call the Big Bang was just a change in phase, like water turning to ice or steam. There are models involving bouncing cosmologies where the universe collapses down to a tiny size and then rebounds back out in a new Big Bang. Or cyclic models where the universe goes through an endless series of big bangs and big crunches, expansion and contraction, over and over again through infinite time. These models would restore the idea of an infinite past, not a linear infinite past with a chain of causes stretching back forever, but a cyclical infinite past with repeating patterns. But here's the thing, here's what makes this so difficult. We don't have strong evidence for any of these pre-Big Bang scenarios. They're speculative, based on incomplete theories. What we do have strong evidence for is that our universe, the space-time we inhabit, began in a hot, dense state about 13.8 billion years ago and has been expanding and cooling ever since. Everything we can observe and measure points to that conclusion. The cosmic microwave background radiation, the afterglow of the Big Bang, is still detectable, filling all of space with a faint microwave hum. The abundance of light elements like hydrogen and helium matches what we'd expect from nucleosynthesis in the early universe. The distribution of galaxies and large-scale structure matches what we'd expect from tiny quantum fluctuations in the early universe being stretched to cosmic size by expansion. So the scientific picture, as far as we can tell from observation, is that the past is finite. Time began with the Big Bang. And before that, well, there is no before in any meaningful sense, or at least not one we can currently access or describe with our physics. That's a remarkable conclusion, right? After thousands of years of philosophical debate about whether time is infinite or has a beginning, science comes along and says, based on actual observations of the universe, that time had a beginning. That's profound. But now let's turn to the other direction. Let's think about the future. If the past is finite, bounded by the Big Bang, what about the future? Does it go on forever, or will it come to an end? And if it goes on forever, what will it be like? Will the universe just keep expanding and evolving forever, or will something else happen? This is where thermodynamics comes into play, that branch of physics that deals with heat and energy and entropy. And entropy is crucial for understanding time and the future. Entropy is a measure of disorder, of the number of ways a system can be arranged, of how spread out and mixed up the energy in a system is. And there's this fundamental law, the second law of thermodynamics, which says that in any closed system, entropy always increases over time. Things get more disordered, more mixed up, more spread out. Heat flows from hot to cold, never the reverse. You can scramble an egg, but you can't unscramble it. Order decays into disorder. This is why time has an arrow, a direction. The past is different from the future, not just because we remember one and not the other, but because there's a fundamental asymmetry built into the laws of physics. Entropy was lower in the past and will be higher in the future. If you see a video of a breaking glass, you immediately know which direction is forward in time. The glass shattering into pieces is the natural direction. Pieces spontaneously assembling into a glass would be running backward, violating the second law. Now, the universe as a whole is a closed system, the biggest closed system there is. So entropy in the universe as a whole must be increasing over time. And this has profound implications for the far future, because if entropy keeps increasing, eventually the universe will reach a state of maximum entropy, a state where all the energy is spread out as evenly as possible, where no work can be done, where nothing interesting can happen. This is called heat death, and it's the ultimate fate of the universe according to thermodynamics. What would heat death look like? Well, it's a bit grim, honestly. All the stars would have burned out, exhausted their nuclear fuel. All the matter would have decayed or been swallowed by black holes. Even the black holes would eventually evaporate through a quantum process called Hawking radiation, named after Stephen Hawking, who discovered it. This process is incredibly slow, taking trillions upon trillions of years for even small black holes and incomprehensibly longer for large ones. But given enough time, all black holes would evaporate, leaving behind just a thin soup of photons and elementary particles spread out over vast distances at a temperature just barely above absolute zero. No structure, no complexity, no life, no thought. Just a cold, dark, empty universe approaching maximum entropy. And this state, this heat death, it would last forever. Once you reach maximum entropy, there's nowhere else to go. Nothing changes anymore because there's no energy gradient to drive change. It's like a clock winding down and finally stopping, except the clock is the entire universe and it never starts again. Time would still exist in some technical sense. Moments would still follow one another, but nothing would happen. No events, no change, just an endless frozen state. Now, that might sound depressing, and in a way it is. The universe, on cosmological timescales, is mortal. It had a birth, it has a life, and it will have a death. Everything we know and care about, every star and planet and living thing, all of human civilization, and everything that might come after us, all of it is temporary, a brief flicker in the cosmic night, destined to fade away into cold darkness. But let's think about the timescales involved here. The universe is currently about 13.8 billion years old. The last stars will burn out in perhaps 100 trillion years, give or take. That's about 10,000 times the current age of the universe. Black hole evaporation takes vastly longer, with supermassive black holes surviving perhaps 10 to the power of 100 years or more, and the approach to true heat death, to absolute maximum entropy, might take even longer still, perhaps 10 to the power of Google years, where a Google is 10 to the power of 100. These numbers are so large they're almost meaningless. They dwarf the current age of the universe by factors so huge that human minds can't really grasp them. So yes, the universe will end in heat death, but that ending is so far in the future that it's almost academic. For all practical purposes, for timescales that are relevant to life and thought and civilization, the future is effectively infinite. Even if intelligent civilizations survive for billions or trillions of years, even if they spread across galaxies and find ways to harvest energy from every possible source, even if they do things we can't imagine with our current technology, they'll still be working with a tiny fraction of the total time available. The future is so vast that it might as well be infinite for anyone actually living in it. And there's another aspect to this that's fascinating. The expansion of the universe isn't just continuing, it's accelerating. This was discovered in the late 1990s through observations of distant supernovae, and it was so unexpected that the discoverers won the Nobel Prize. Something is pushing the universe to expand faster and faster, and we call that something dark energy. We don't really know what dark energy is. It might be a property of space itself, a cosmological constant as Einstein once proposed, or it might be some kind of field or energy that permeates all of space. But whatever it is, it's winning the battle against gravity, pushing galaxies apart at an ever-increasing rate. This accelerating expansion has consequences for the far future. It means that distant galaxies are receding from us faster and faster, and eventually they'll be receding faster than light can travel through the expanding space between us. Once that happens, we can never see them again, never reach them, never communicate with them. They effectively exit our observable universe forever. Over time, more and more galaxies will cross this cosmic horizon and disappear from view. Billions of years from now, an observer in our local group of galaxies, assuming anything is still around to observe, would see a universe that appears much emptier, with only the nearby galaxies visible, everything else having receded beyond the horizon. So the future isn't just about entropy and heat death, it's also about cosmic isolation. The observable universe will shrink, in a sense, even as the universe as a whole continues to expand. And this raises interesting questions about what future civilizations would be able to learn about cosmology. If all the distant galaxies have disappeared beyond the horizon, if the cosmic microwave background has been redshifted away to nothing, what evidence would remain of the Big Bang? What would future scientists be able to figure out about the history and nature of the universe? They might look at the universe and conclude it's eternal and unchanging, never realizing that it had a dramatic beginning and has been evolving all along. But let me come back to this question of infinity, because there's a deeper puzzle here that we haven't addressed. Even if the future lasts forever, even if time goes on without end, there's something strange about the idea of infinite future time in a universe governed by thermodynamics and entropy. Because here's the thing, if you have infinite time, then anything that can happen will happen. Not just once, but infinitely many times. This is the idea behind Boltzmann brains, named after the physicist Ludwig Boltzmann. The argument goes like this: in a universe approaching heat death, approaching maximum entropy, there will still be random quantum fluctuations, little temporary decreases in entropy that happen by chance. These fluctuations are incredibly rare, but given infinite time, they will happen. And if you wait long enough, eventually there will be a fluctuation large enough to create a conscious observer, a brain with false memories of a past that never happened, floating in the void. Such a brain, called a Boltzmann brain, would exist for just a moment before dissolving back into chaos. Now here's the disturbing part. If the future is infinite, then Boltzmann brains will be created infinitely many times. And there will be vastly more Boltzmann brains than normal evolved brains like ours, because Boltzmann brains require much smaller fluctuations in entropy. It's much more likely for a random fluctuation to create a single disembodied brain than to create an entire universe with galaxies and stars and planets and billions of years of evolution leading to intelligent life. So if you pick a conscious observer at random from all the observers that will ever exist in an infinite future, you're overwhelmingly likely to pick a Boltzmann brain. And if you're overwhelmingly likely to be a Boltzmann brain, then you can't trust your memories or perceptions. Everything you think you know about the past, about the universe, about science and history, all of it could be a false memory implanted in a momentarily fluctuated brain. This leads to a kind of skeptical nightmare where science undermines itself, where the very theories that predict an infinite future also predict that you can't trust your observations or reasoning. Physicists hate this conclusion, and there's been a lot of debate about how to avoid it. Maybe the future isn't actually infinite. Maybe the universe will undergo some kind of quantum transition to a different state, preventing the eternal heat death scenario. Or maybe our understanding of entropy and probability in an infinite universe is wrong somehow. Or maybe we need to think about the multiverse, about the possibility that our universe is just one of many, and we need to consider the probability of observers across all universes, not just our own. This is still an active area of research, with no clear consensus on the right answer. But the Boltzmann brain paradox illustrates something important about the difficulty of thinking about infinite future time. Infinity doesn't just mean a really long time. It means that probability breaks down in weird ways. Anything with a non-zero probability will happen infinitely many times. And when you try to make statistical predictions or calculate likelihoods, you run into paradoxes and contradictions. Infinity is subtle, counterintuitive, and deeply strange. Let's shift gears a bit and think about infinity from a different angle. So far, we've been talking about time as if it's just one thing, a single timeline stretching from past to future. But there's another way to think about time, one that comes from taking Einstein's relativity seriously. It's called the block universe or eternalism, and it's the idea that all of time, past, present, and future, exists equally real all at once. You see, in special relativity, the division of events into past, present, and future is relative to your frame of reference. Different observers moving at different speeds will disagree about which events are simultaneous, about which events are in the past and which are in the future. The only thing everyone agrees on is the space-time interval between events, a combination of space and time that's the same for all observers. This suggests that space-time is more fundamental than space or time separately, and that the flowing present moment, the now that we experience, isn't a fundamental feature of reality, but rather a subjective experience of observers. In the block universe view, all moments of time exist equally. The past hasn't ceased to exist. The future hasn't yet come into being. Instead, all moments are laid out in space-time like frames in a film strip, all existing together. Your birth, your childhood, This moment of reading or listening to these words, your death and everything after, all of it exists, has always existed, will always exist in the eternal four-dimensional structure of space-time. Time doesn't flow, we just have the illusion of flow because our consciousness experiences one moment after another. Now, if you accept the block universe, then the question of whether the past is infinite or the future is endless takes on a different character. It's not about whether time goes on forever, it's about the structure and extent of the space-time manifold. Does space-time have a boundary in the past, the Big Bang? Does it have a boundary in the future, or does it extend infinitely? And if it extends infinitely, then the entire infinite future already exists in some sense, just as real and present as this moment, even though we haven't experienced it yet. This is philosophically challenging, right? Because it seems to conflict with our experience of time as flowing, of the future as open and undetermined. If the future already exists in the block universe, then everything is predetermined, already laid out. There's no real choice, no real possibility of things being different. Your entire life, every decision you make, every thought you have, it's all already there in the space-time structure, fixed and unchangeable. That's a deeply unsettling idea for many people because it seems to eliminate free will, to make everything you do and experience just a predetermined part of an eternal, unchanging pattern. But there are counter-arguments. Some philosophers argue that even in a block universe, there can be a meaningful sense of agency and choice, because your decisions are part of what determines the structure of the block universe. It's not that the future is already decided apart from your choices. It's that your choices are part of the story of how the future is what it is. Others reject the block universe entirely, arguing that the flowing present is real and fundamental, and that relativity doesn't actually require us to give up on the idea of becoming, of time genuinely passing. And then there's quantum mechanics, which throws another wrench into the whole discussion. Quantum mechanics tells us that the future isn't determined by the present, at least not completely. When a quantum measurement happens, when a particle's position is measured or a radioactive atom decays, the outcome is truly random, not determined by anything prior. There are probabilities, yes, calculated from the wave function, but the specific result is genuinely unpredictable, even in principle. This quantum indeterminacy seems to conflict with the block universe picture where everything is already laid out. How can the future already exist if it's not even determined yet? Some interpretations of quantum mechanics get around this by proposing that all possible outcomes happen just in different branches of the universe. This is the many worlds interpretation, where every quantum measurement causes the universe to split into multiple copies, each with a different outcome. In one branch, the particle goes through the left slit. In another branch, it goes through the right slit, and both branches are equally real. If many worlds is correct, then the future isn't just one thing. It's a vast branching tree of possibilities, all existing, all real. And infinity becomes even more complex, because not only might time extend infinitely into the future, but at every moment there might be infinitely many branches, infinitely many versions of you, experiencing infinitely many different futures. The totality of existence becomes vastly larger than we ever imagined, an infinite number of parallel timelines all coexisting. But we don't know if many worlds is correct. It's one interpretation among several, and there's no experimental way to definitively prove or disprove it. Other interpretations of quantum mechanics preserve a single timeline, but accept that the future is genuinely open until it happens, that there's real randomness built into the fabric of reality. And some physicists think we're still missing something fundamental about quantum mechanics, that there's a deeper theory waiting to be discovered that will make sense of all the weirdness. Let me shift again and think about what infinity means for meaning itself, because all of this talk of infinite past or infinite future, heat death and Boltzmann brains and block universes, it can feel abstract and remote from everyday life. But I think it actually touches on something deeply personal, something about how we find meaning and purpose in our finite lives within a possibly infinite cosmos. If the universe had no beginning, if it has existed forever, then everything that has happened is just one moment in an infinite sequence. Your life, all of human history, the entire lifetime of Earth and the Sun. It's all infinitesimal against the backdrop of infinite time. And if the future is infinite, if the universe will exist forever, then everything we do is similarly insignificant. Whatever we accomplish, whatever legacy we leave, it will eventually be erased by time, forgotten in the approach to heat death, meaningless in the grand scheme of eternity. This can lead to a kind of cosmic nihilism, a sense that nothing matters because it's all temporary against infinite time. But I think there's another way to look at it, a way that's more life-affirming. Because the fact that we exist at all, that the universe has produced beings capable of thought and feeling and love and curiosity, beings who can contemplate their own existence and the nature of time itself, that's remarkable regardless of how long it lasts. The meaning of your life doesn't come from lasting forever. It comes from the experiences you have, the relationships you form, the understanding you gain, the beauty you create and appreciate. Think about a piece of music. It exists in time, it has a beginning and an end, and when it's over, it's gone, just a memory. But the fact that it ends doesn't make it meaningless while it plays. The beauty and emotion of the music, the way it moves you, that's real and valuable, even though it's temporary. Maybe our lives are like that, beautiful and meaningful precisely in their temporariness, their finitude against the vast scale of cosmic time. And there's something else, something about the relationship between finite and infinite that's worth considering. The universe might be infinite in extent or duration, but we are finite. We have a limited lifespan, a limited perspective, a limited understanding, and yet within our finitude, we can grasp concepts of infinity. We can imagine time stretching endlessly. We can conceive of numbers growing without bound. We can contemplate the vastness of space and time. That capacity, that ability to transcend our own limitations in thought, if not in reality, that's a kind of miracle, isn't it? Mathematicians work with infinity all the time. They distinguish between different types of infinity, different cardinalities as they call them. Some infinities are larger than others in a precise mathematical sense. The number of integers is infinite, but the number of real numbers is a larger infinity. And there might be infinities larger still, hierarchies of infinities extending upward without limit. This mathematical framework gives us tools to think rigorously about infinity, to make precise statements and prove theorems, even though we can never actually complete an infinite process or count an infinite collection. And this mathematical infinity, these abstract concepts that mathematicians play with, they might actually describe aspects of physical reality. If space is truly infinite in extent, if there are infinitely many stars and galaxies extending in all directions forever, then physical infinity exists, not just as a mathematical abstraction, but as a concrete reality. Or if the many worlds interpretation is correct, if there are infinitely many branches of the universe, then again we have physical infinity. Or if time extends infinitely into the past or future, that's another form of physical infinity. But we don't know for sure. We can't observe infinity directly because we're finite beings with finite instruments making finite measurements. We can see only a finite portion of the universe, the observable universe bounded by the cosmic horizon. We can measure only finite intervals of time with finite precision. Infinity always lies beyond our direct grasp, something we extrapolate to but never actually reach. Let's think about the anthropic principle for a moment, because it's relevant to this question of infinite past and future. The anthropic principle, in its weak form, just says that we observe the universe to have properties compatible with the existence of observers, because if it didn't have those properties, we wouldn't be here to observe it. That sounds like a tautology, and in a way it is, but it has interesting implications when you think about it carefully. For instance, the universe has certain fundamental constants, like the strength of gravity or the mass of the electron or the cosmological constant. And these constants seem to be finely tuned, meaning that if they were even slightly different, the universe would be radically different and probably wouldn't support life. If gravity were a bit stronger, stars would burn out too quickly for life to evolve. If it were a bit weaker, stars might never form at all. If the cosmological constant were much larger, the universe would have expanded too rapidly for galaxies to form, and so on. Now, one way to explain this fine-tuning is to invoke a multiverse. If there are infinitely many universes, or an enormously large number of them, each with different values for the fundamental constants, then it's not surprising that we find ourselves in one of the rare universes where the constants are right for life. We couldn't exist in the others, so of course we observe a life-permitting universe. The anthropic principle, combined with the multiverse, dissolves the puzzle of fine-tuning. But notice what this does to the question of infinity. If there's a multiverse with infinitely many universes, then we've moved from asking whether our universe is infinite in time or space to asking about whether the totality of existence, the multiverse itself, is infinite. And the answer might be yes, depending on the details of how the multiverse is generated. In eternal inflation models, for instance, the process of creating new universes through inflation never stops. It goes on forever, producing infinitely many pocket universes, each with potentially different properties. So infinity keeps coming back, keeps showing up in different guises. We try to get a handle on it, to understand whether the past is infinite or the future is infinite or space is infinite, and we find that the question shifts, becomes more complex, opens up new questions rather than providing final answers. And maybe that's appropriate. Maybe infinity, by its very nature, is something we can never fully grasp or completely resolve. We can think about it, reason about it, develop mathematical frameworks and physical theories, but the actual infinite always exceeds our finite minds. We're like people trying to map an infinite territory with finite resources. We can explore regions, make progress, understand parts of it, but we can never complete the map, never see the whole picture. There's a humility in that, right? An acknowledgement of our limitations as finite beings trying to understand a possibly infinite cosmos. But there's also a kind of courage, a determination to keep asking questions and seeking understanding, even when we know we can't reach final answers. Science is always provisional, always open to revision in light of new evidence. Philosophy grapples with perennial questions that might not have definitive resolutions. And yet we keep at it, keep thinking and observing and wondering, because that's what it means to be human, to be conscious creatures who care about truth and understanding. Let me circle back to thermodynamics and entropy for a moment, because there's another aspect of this that's fascinating and relevant to the question of infinite future. I mentioned earlier that the second law of thermodynamics says entropy always increases in a closed system. But here's something puzzling. If you look at the microscopic laws of physics, they're time reversible. For every process that can happen going forward in time, the reverse process can happen going backward in time. If you filmed a collision between two particles and played it backward, the reverse collision would obey the same laws of physics. So where does the arrow of time come from? Why do we see entropy increasing in one direction but not the other? Why does time have an arrow at all? The answer, physicists think, has to do with initial conditions. The universe started in a very special low entropy state at the Big Bang, and entropy has been increasing ever since simply because there are vastly more high entropy states than low entropy states. It's statistically overwhelmingly likely for entropy to increase, even though the microscopic laws are time reversible. But this explanation raises a new question. Why did the universe start in such a special low entropy state? What determined those initial conditions? If you trace everything back to the Big Bang, you find that the entropy at the beginning was extremely low, far from the maximum possible entropy. The universe could have started in a high entropy state, a state of chaos and disorder, and if it had, nothing interesting would have happened. No stars would form, no galaxies, no planets, no life, no observers to wonder about entropy. The universe would have been born dead, in a sense. So the fact that the universe started with low entropy is crucial for everything that follows, for the entire history of increasing complexity and structure, and eventually life and consciousness. But why? Why that initial state rather than some other? There's no clear answer within the framework of the Big Bang model. The initial conditions are just put in by hand, assumed as a starting point, not explained by the theory. Some physicists think this is where quantum gravity or theories of the multiverse might help. Maybe there's a deeper explanation for why the universe started with low entropy, something to do with the quantum creation of the universe or the selection effects in a multiverse where we can only exist in the rare regions with low initial entropy. But these are speculative ideas, not yet well developed or tested. And there's another strange thing about entropy and time. If the future extends infinitely, if we reach heat death and maximum entropy and then just stay there forever, then most of the history of the universe, most of the infinite future, will be spent in this dead state. All the interesting stuff, the stars and galaxies and life and thought, all of it happens in a brief transient phase at the beginning, infinitesimal compared to the infinite duration of heat death. It's like the universe is born, lives a brief interesting life, and then spends eternity dead. That's a strange and rather melancholy picture. Unless, of course, there are those quantum fluctuations we talked about earlier, the Boltzmann brains, and possibly larger fluctuations that create temporary pockets of low entropy. Then, the infinite future wouldn't be completely static. There would be rare moments of interesting things happening, isolated oases of order in the vast desert of maximum entropy. But these would be incredibly rare, separated by unimaginable gulfs of time. And as I mentioned earlier, this leads to the puzzle of why we seem to be in a normal universe rather than a Boltzmann fluctuation. Let's think about cultural and historical perspectives on infinite time for a moment, because different cultures and eras have thought about this very differently, and those differences are revealing. In ancient Greece, as I mentioned, there was debate between those who thought time was infinite and those who thought it had a beginning. Aristotle leaned toward eternal time, while later thinkers influenced by Christianity adopted the idea of creation and a beginning of time. In medieval Europe, the dominant view was that time began with God's creation and would end with the Last Judgment and the establishment of eternity, a timeless realm beyond the temporal world. Time was seen as finite, bounded by these events, with all of history playing out between creation and apocalypse. This gave time a narrative structure, a meaning and purpose, with history moving toward a divinely ordained end. In contrast, Hindu and Buddhist cosmologies often featured vast cyclical time, with the universe going through enormous cycles of creation and destruction. The concept of a kalpa, a cosmic cycle lasting billions of years, far exceeded the Judeo-Christian timeline and approached something like infinity through endless repetition. These traditions were more comfortable with the idea of time stretching in both directions without absolute beginning or end, at least in the temporal realm, though they also often posited a timeless, transcendent reality beyond the cycle of time. Indigenous cultures around the world have had their own varied concepts of time, some more cyclical, some more linear, some emphasizing connection between past and future through ancestors and descendants. The Western scientific view of linear time with a definite beginning and indefinite or infinite future is just one possibility among many, and it's shaped by particular historical and philosophical influences. And it's worth noting that our modern scientific picture, with its Big Bang beginning and heat death future, wasn't inevitable. It's based on specific observations and theories that could have turned out differently. If Hubble hadn't discovered the expansion of the universe, if Einstein's cosmological constant had been larger, if the cosmic microwave background hadn't been detected, we might have a very different understanding of cosmic history. Science is contingent on evidence, and the evidence we have points in a particular direction, but there's always the possibility of surprises, of new discoveries that force us to revise our models. Think about dark energy and dark matter, for instance. Together, they make up about 95% of the total mass energy of the universe, and we don't really know what they are. Dark matter seems to be some kind of particle that doesn't interact with light, but does exert gravitational effects, clustering around galaxies and holding them together. Dark energy, as I mentioned, seems to be causing the accelerated expansion of the universe, but the precise nature of both remains mysterious. What if our understanding of dark energy is incomplete? What if it's not a constant, but changes over time? Some models propose that dark energy might decay or transform, potentially leading to different future scenarios than simple eternal expansion and heat death. Maybe the expansion will reverse, leading to a big crunch where the universe collapses back down to a singularity. Or maybe dark energy will strengthen, leading to a big rip where the accelerating expansion eventually tears apart galaxies, stars, planets, and even atoms, or maybe something else entirely that we haven't thought of yet. The point is, our understanding of the far future is based on extrapolating current physics into vastly different conditions and timescales, and there's a lot of uncertainty in that extrapolation. We're more confident about the past because we have evidence like the cosmic microwave background and nucleosynthesis that constrain the models. But the future is more open, more uncertain. We can make predictions based on our best current theories, but we should hold those predictions tentatively, ready to revise them as we learn more. Let me talk about time in quantum mechanics a bit more, because it's genuinely strange and relevant to our question. In quantum mechanics, time plays a different role than in classical physics. In classical mechanics, time is a parameter, something that just ticks along uniformly while states of the system evolve according to deterministic laws. But in quantum mechanics, there's no time observable, no quantum operator corresponding to time, in the same way there are operators for position and momentum. Instead, time appears as a background parameter in the Schrödinger equation that governs how quantum states evolve. But there are deep puzzles about how to reconcile this treatment of time with general relativity, where time is part of the dynamical space-time fabric. In quantum gravity, whatever form it takes, we expect that time itself might be emergent, arising from something more fundamental rather than being a basic ingredient. Some approaches to quantum gravity, like loop quantum gravity, suggest that space-time is discrete at the Planck scale, made up of tiny quantum chunks, rather than being a smooth continuum. If that's right, then time itself is quantized, coming in discrete moments separated by the Planck time. There would be a smallest possible interval of time, and the idea of infinite past or future would have to be reinterpreted in terms of an infinite number of discrete moments rather than a continuous flow. Other approaches, like string theory, work with extra dimensions beyond the familiar three of space and one of time. In some versions of string theory, there might be additional time-like dimensions, though these are usually compactified or treated in special ways to avoid paradoxes. The point is, our intuitive idea of time as a single one-dimensional parameter might be an approximation, valid at everyday scales, but breaking down in more extreme conditions. And then there's the Wheeler-DeWitt equation, an attempt to describe the quantum state of the entire universe. In this equation, time doesn't appear at all. The wave function of the universe is static, timeless. The evolution and change we observe emerge somehow from correlations within this timeless quantum state. This is deeply puzzling and counterintuitive. How can there be time? How can things change if the fundamental description is timeless? These are open questions, problems at the frontier of theoretical physics, and they suggest that our understanding of time, even with all the progress we've made from Newton to Einstein to modern cosmology, is still incomplete. There are deeper layers to uncover, more fundamental principles to discover. The question of whether the past is infinite or the future is endless, these might not even be the right questions at the deepest level. Maybe time itself is emergent. Maybe our whole framework of thinking about past and future needs to be revised in light of quantum gravity. But even as we acknowledge these uncertainties and open questions, there's still value in thinking through the implications of what we do know, in taking our best current theories seriously and seeing where they lead. Because that's how science makes progress, by pushing ideas to their limits, finding where they break down, and using that knowledge to build better theories. Let me think about the subjective experience of time for a moment. Because even if time is an illusion in some deep sense, even if the block universe is real and all moments exist equally, we still experience time as flowing, the present moment as real, and the past as gone, and the future as yet to come. That experience is part of what it means to be conscious, to be a self that persists through time and remembers and anticipates. And there's something strange about this experience when you think about it. You right now, reading or hearing these words, you exist for just a moment, an instant. The you of a second ago is already gone, existing only in memory. The you of a second from now doesn't exist yet, and yet there's a continuity, a sense that you're the same person persisting through time, even though you're constantly changing, constantly being replaced by a slightly different version of yourself. Personal identity over time is a philosophical puzzle. What makes you the same person as you were 10 years ago? It's not the same atoms. Those have been replaced many times over. It's not the same thoughts or memories. Those have changed. It's not even the same body in any straightforward sense. And yet there's a continuity of consciousness. a narrative thread that connects past and future selves. We construct a story of our lives, a sense of self that extends through time, and that story is how we make sense of our existence. And this connects to the larger questions about infinite time, because if the future is infinite, or even just very long, what does that mean for personal identity and continuity? If you could somehow survive indefinitely, preserving your consciousness across vast stretches of time, would you still be you? As memories fade and accumulate, as you change and grow and adapt across millions or billions of years, at what point do you become someone different? Is there a coherent self that can extend infinitely into the future, or does the very idea of personal identity break down over sufficiently long timescales? These are not just abstract philosophical questions. They become practical if we ever develop technologies for radical life extension or mind uploading or other ways of preserving consciousness beyond the normal human lifespan. If we could live for thousands or millions of years, how would that change us? Would we become something other than human? Would we lose the sense of meaning that comes from finitude, from knowing our time is limited? Some transhumanist dream of immortality, of extending life indefinitely through technology. But is that desirable? Would infinite life be boring, repetitive, eventually meaningless? Or would there always be new experiences, new things to learn, new ways to grow? It's hard to say because we have no experience of what it's like to live for even 1,000 years, let alone infinitely. Our intuitions about what makes life meaningful are shaped by our finite lifespans, by the scarcity of time, by the knowledge that we must choose how to spend our limited years. Take away that finitude and the whole context changes. There's a story, I think it's from Borges, about a man who becomes immortal and eventually becomes tired of existence, bored by the endless repetition, desiring death as the only remaining novelty. It's a cautionary tale about the possible downsides of immortality. But there are also visions of immortality where continued growth and change make each moment valuable, where the joy of existence doesn't fade with time. Which vision is right? We don't know, and maybe we can't know until we actually try it, if we ever do. But bringing it back to the cosmic scale, the universe's far future, that question of meaning in the face of infinite time, it's relevant. If civilizations survive long enough, if they spread across the galaxy or beyond, if they find ways to harvest energy from black holes or harness the expansion of space or whatever other exotic technologies might be possible, they'll face these questions. How do you maintain purpose and meaning over billions or trillions of years? How do you avoid stagnation and decay, not just physical entropy, but psychological and cultural entropy? Science fiction has explored these themes. Isaac Asimov's The Last Question is a beautiful short story about entropy and the far future, about whether the increase of entropy can be reversed. It follows humanity and its increasingly advanced AI descendants through eons as stars burn out and the universe approaches heat death, with the ultimate question remaining unanswered until the very end. It's a hopeful story in its way, suggesting that even in the face of cosmic entropy, consciousness and intelligence might find a way forward. Or consider Olaf Stapledon's Star Maker, which takes an even longer view, describing the history of the universe across vast stretches of time, countless civilizations rising and falling, eventually merging into a cosmic mind that perceives the entire history of the cosmos all at once. It's a vision of time and consciousness on the largest possible scale, grappling with questions of meaning and purpose in an immense and possibly eternal universe. These stories, while fiction, are valuable thought experiments. They help us imagine possibilities, explore implications, think through what infinite or near infinite time might mean for consciousness and civilization. And they remind us that these questions aren't just academic abstractions. They touch on the deepest concerns about who we are and why we're here. Let me think about one more scientific angle, the possibility of a cyclic universe. I mentioned this earlier, but it's worth exploring in more depth because it offers a different way out of the puzzle of infinite past. If the universe goes through cycles, expanding and contracting, Big Bang, followed by Big Crunch, followed by another Big Bang, then in some sense time might be infinite without requiring an infinite linear progression. The idea of a cyclic universe is ancient, as I mentioned, but there are modern scientific versions. The ekpyrotic model, for instance, proposes that our Big Bang was the result of a collision between two higher dimensional membranes, and this collision might repeat cyclically. Or there's the conformal cyclic cosmology proposed by Roger Penrose, where the infinite future of one aeon of the universe becomes the Big Bang of the next, with time extending infinitely through a series of connected aeons. These models are speculative and face various challenges. For a cyclic model to work, you need some way to reset the entropy at the start of each cycle. Otherwise, entropy just accumulates and the cycles can't continue indefinitely. You need some mechanism to trigger the bounce from contraction to expansion without hitting a singularity. And you need to match observations like the cosmic microwave background and the abundance of elements which constrain what the early universe was like. But if a cyclic model is correct, it would profoundly change how we think about the infinite past and future. Instead of a single arrow of time from Big Bang to heat death, we'd have an endless cycle, no beginning and no end, just eternal recurrence on the grandest scale. Each cycle might be similar or might be different, with different physical constants or different histories. We might be living in just one cycle among infinitely many, with infinitely many versions of us, similar or different, existing in past and future cycles. That's a dizzying thought, right? An infinity of cycles, each with its own history, its own civilizations, its own triumphs and tragedies. And if the cycles are truly identical, repeating the same events over and over, then we've lived this exact life infinitely many times before and will live it infinitely many times again. That's the idea of eternal return that fascinated Nietzsche, who saw in it both a terrifying burden and a liberating philosophy. If every moment will recur infinitely, then every moment has infinite weight, infinite significance. We should live each moment as if we'd will it to recur forever. But do we have evidence for cyclic models? Not really, not yet. The observations support a single Big Bang followed by ongoing expansion. There are hints, anomalies in the cosmic microwave background that some researchers think might be echoes of a previous cycle, but these are controversial and not widely accepted. Most cosmologists think the data fits the standard model of a single Big Bang and ongoing expansion, though they're open to alternatives if new evidence emerges. And even if the universe is cyclic, there are versions where the cycles had a beginning, where there was a first cycle that started the pattern, and versions where the cycles extend infinitely into the past. So even within cyclic models, the question of infinite past isn't fully resolved. It's pushed back, reformulated, but not eliminated. There's also the question of what, if anything, persists across cycles. If entropy is reset, if the universe is effectively reborn with each cycle, then there's no causal connection between cycles, no information transfer, no way for one cycle to influence the next. Each cycle would be effectively a separate universe, and the infinity of cycles would be more like the infinity of parallel universes in a multiverse than a true temporal infinity. The word cycle might even be misleading because it suggests continuity and connection, whereas what we'd really have is a series of disconnected universes sharing some mathematical structure. But I'm speculating now, going beyond what the science can currently tell us. And that's important to acknowledge, to distinguish between what we know with confidence, what we suspect but aren't sure of, and what is pure speculation or philosophy. The boundary between science and philosophy is blurry here because we're asking questions that might not have definitive empirical answers, questions that require interpretation of our best theories and extrapolation beyond what we can observe. What can we say with confidence? We can say that the observable universe began in a hot, dense state about 13.8 billion years ago and has been expanding and cooling ever since. We can say that this expansion is accelerating due to dark energy. We can say that the laws of thermodynamics predict that the universe will eventually reach a state of maximum entropy if the current trends continue. We can say that general relativity describes space-time as a unified whole, and that quantum mechanics introduces fundamental indeterminacy and challenges our classical notions of causation and time. Beyond that, we're making extrapolations and interpretations. Is there something before the Big Bang? We don't know. Will the expansion continue forever? probably, based on current evidence, but there's uncertainty about dark energy's behavior in the far future. Does the block universe correctly describe reality? That's more a philosophical question than a scientific one because we can't directly test the existence of other times. Is consciousness affected by the deep nature of time? We don't know because we don't yet have a good scientific theory of consciousness. And I think there's something valuable in acknowledging these limits, in being honest about what we don't know. It's tempting to overreach, to claim more certainty than we have, to present our current theories as final truth. But science has been wrong before, and it will be wrong again. Not wrong in the sense that it's all false, but wrong in the sense that our current theories are approximations, good within their domain of validity, but breaking down at extremes or needing revision in light of new evidence. Newton's physics wasn't wrong exactly, it's just incomplete. It works beautifully for everyday situations, but it fails for very fast motion or very strong gravity. Einstein's relativity corrects and extends Newton, giving us a better approximation to truth. But even Einstein's theory is incomplete, failing to reconcile with quantum mechanics. We need an even better theory, quantum gravity, that will correct and extend Einstein. And even that theory, when we find it, might not be final. There might be deeper levels still, turtles all the way down, or at least turtles for a very long way down. So when we talk about infinite past and endless future, we're working at the limits of our knowledge, trying to extrapolate from what we know to what we suspect might be true. And we should hold our conclusions tentatively, with appropriate humility, ready to revise in light of new understanding. That doesn't mean we shouldn't think about these questions or try to answer them. It just means we should be clear about the status of our answers, the difference between well-supported scientific conclusions and speculative extrapolations. And there's beauty in that uncertainty, in the open-ended nature of inquiry. We're exploring the edges of knowledge, venturing into territory where the map is incomplete or non-existent. That's where the excitement is, where new discoveries await. If we already knew everything about the infinite past and endless future, what would be left to learn? The mystery is part of what makes it fascinating. Let me return one last time to the human dimension of all this, because ultimately that's what matters most to us. We're not just disembodied intellects thinking about abstract cosmology. We're finite creatures living finite lives in this vast, possibly infinite cosmos. And the question of infinite time, whether in the past or future, touches on how we understand ourselves and our place in the universe. If the past is finite, if there was a beginning to time, then in some sense the universe has a story, a narrative arc from beginning to current state. We're part of that story, however small our role might be. Our existence is contingent on a long chain of events stretching back to the Big Bang, every step necessary for us to be here. There's a kind of connection, a historical thread linking us to the origin of everything. If the future is effectively infinite, or at least vastly longer than any timescale we can relate to, then our moment in time is extraordinarily brief, a flash in the cosmic night. Everything we do, everything we care about, will eventually be gone, erased by time and entropy. That can seem depressing, nihilistic, as if nothing we do matters, but I think there's another way to see it, a more affirmative perspective. Yes, we're small and temporary against the backdrop of cosmic time, but we're also remarkable, improbable, precious precisely because of that impermanence. The universe, for a brief moment, has become aware of itself through us. We can think about the Big Bang and the heat death. We can contemplate infinity and feel wonder and awe. That's miraculous in its way. And the fact that it's temporary doesn't diminish it. A sunset is beautiful even though it lasts only minutes. A life is meaningful even though it lasts only decades. The value isn't in the duration, it's in the quality, the experience, the consciousness and connection and growth that happens in the time we have. We don't need to last forever to matter. We matter now, in this moment, to ourselves and each other. Maybe the universe will end in cold darkness. Maybe consciousness will eventually fade away as entropy reaches its maximum. Or maybe there will be Boltzmann brains. Or maybe there will be cyclic renewal. Or maybe something we haven't imagined. We don't know. But what we do know is that right now, right here, we're alive and aware and able to think about these profound questions. That's a gift, an opportunity, regardless of what came before or what comes after. And there's something about the finite perspective that makes meaning possible. If you lived forever, would anything be urgent? Would any choice be truly significant? It's the fact that time is limited, that we have to choose how to spend our days, that gives weight to our decisions. We can't do everything, be everywhere, experience all possible lives. We have to choose, and those choices matter because they shape who we become and how we spend the one life we have. So even if the future is infinite in principle, it's finite for us, for any individual consciousness. We experience time from within as a flowing present, with a limited past in memory and an uncertain future ahead. And that limited perspective is what makes our existence meaningful. We're not infinite beings contemplating eternity from outside. We're finite creatures embedded in time, making our way through it moment by moment, doing our best to understand and to live well. The infinite past and endless future, these vast scales of time, they provide context. They show us how small we are in the grand scheme, but they don't diminish our significance, they highlight it. We're the universe thinking about itself, matter and energy, arranged in such a way as to be aware, to care, to wonder. That's not nothing, that's everything really. And maybe that's the thing about infinity, about these questions of eternal time. They remind us of our place, our scale, our finitude. But they also invite us to transcend that finitude in thought, to reach beyond ourselves, to connect with something larger. Whether that larger thing is the cosmos itself, or the accumulated knowledge of humanity, or the community of conscious beings across space and time, or some spiritual dimension beyond the physical, there's a reaching upward, outward, a desire to be part of something more than just our individual limited existence. Philosophy and religion have always grappled with these themes, with the relationship between finite and infinite, temporary and eternal, individual and universal. Science adds new dimensions to these ancient questions, giving us concrete knowledge about the history and future of the universe, but it doesn't eliminate the questions. If anything, it makes them deeper, more complex, more fascinating. We live in an age where we know so much more than our ancestors did about the nature of time and the universe. We can trace cosmic history back to the first fraction of a second after the Big Bang. We can predict the far future with some confidence based on thermodynamics and cosmology. We have theories and evidence and mathematical frameworks. And yet, the fundamental mysteries remain. Why is there something rather than nothing? Why does time flow forward? What is consciousness? What gives life meaning in a possibly infinite cosmos? These questions might not have final answers, or at least not answers that we can reach with our current understanding. But the asking itself is valuable, the wondering and thinking and exploring. That's what makes us human, what distinguishes us from mere matter-obeying physical laws. We're matter that asks questions, that seeks understanding, that cares about truth and meaning. So I started by thinking about the infinite past and the endless future, about whether time goes back forever or had a beginning, whether it goes on forever or will end. And we've explored what science tells us, what philosophy suggests, what the possibilities are. The scientific picture says the past is finite, beginning with the Big Bang, but there are speculative ideas about pre-Big Bang scenarios. The future appears to be effectively infinite, or at least vastly long, stretching toward heat death and maximum entropy, though with uncertainties about dark energy and quantum fluctuations and possible cycles. But more than the specific answers, what strikes me is the journey of thinking through these questions, the way they connect to everything else we care about. Time isn't just an abstract parameter in equations, it's the medium of our existence, the framework within which we live and love and learn. Understanding time means understanding ourselves, our place in the cosmos, what it means to be temporary beings in a possibly eternal universe. And maybe the answer isn't a single definitive statement about whether the past is infinite or the future is endless. Maybe the answer is more subtle, acknowledging the limits of our knowledge, the different perspectives we can take, the various possibilities that remain open. We can hold multiple ideas in tension, exploring each one while remaining uncertain about which is ultimately correct, if any. That's the scientific attitude, really. Not claiming absolute certainty, but building models and testing them and revising them and always staying open to new evidence and new ideas. It's an attitude of humility combined with curiosity, acknowledging what we don't know while actively working to know more. And it's an attitude that serves us well, not just in science, but in life generally, approaching the world with wonder and openness rather than rigid certainty. The infinite past and the endless future, they stretch beyond our grasp, always exceeding our attempts to fully comprehend them. But we can glimpse them, think about them, feel the weight and wonder of them. And in doing so, we connect with something larger than ourselves, something that was here before us and will be here after us, the vast, strange, beautiful universe that gave us birth and will one day reclaim us. We're part of it, made of it, and for this brief moment, aware of it. And that awareness, that consciousness, that's the real miracle, the thing that makes all the questions worth asking.